Okay, just some general notes on exponentials and logs, and then I'll go on the last part, which involves looking at some graphs. So firstly, if let's just summarize. If I've got a function where I've got a to the power of x, I know that's an exponential function, then the inverse of that function is written as log of x base a. Another way to express the same idea is to say if y equals a to the power x, then x equals log of y base a. I started off this whole topic with this example where I had 3 squared equals 9, so the power comes down, 2 equals log 9 base 3. You can obviously this comes from taking the logs of both sides. If you're working base 10, you'll have you'll take the logs of both sides, so you'll have log 9 divided by log 3 equals 2 to the base 10, but if you change the bases, then you get this value here. Right, the graph of the exponential function looks like this. So you got a to the power x, so that's increasing exponentially, and the inverse, so it will be a reflection of the line y equals x, is given by this green line over here, and the intercept over here, we know when x equals 0, so x coordinate is going to be 0. Anything to the power 0 is just 1, so it's going to be 0, 1. And then anything which is reflected in the line y equals x is simply inverted. So the 0, 1 inverts to 1, 0. You can also check this. If you have y equals to 0, then x will have to be 1. And no matter what base it is, the log of anything, of the log of 1 to any base gives you 0. Right, some might be wondering what are logs exactly, and how does it relate to powers and what we're doing. Logs is a way of counting, essentially, counting numbers, and it's like it focuses on if you pick a particular base, then it works within that base. So let's look at base 3, for example, and if I write the numbers out, so from 3, I've got 0, 1, 2, 3, 4, 5 as my powers, and then obviously I can go on and on and on, and I've got 1, 3, 9, 27, 81, 2, 4, 3. And say I was to take the log of 1 base 3, if I put that in a calculator, if you want to check, otherwise I get 0. And then if you put 3 in there, you get 1. If you put 9 in there, and remember 9 is 3 squared, you get 2. And then if you put 27, you get 3, and on and on and on. So essentially what it does, it gives you the power. Okay, the power that you would put on top of 3 to get the number that you put inside the log function. So in base 3, it's like it's in mode 3, and it's perceiving or working out these numbers in terms of this base. And so it helps with working with really, really large numbers or very, very small numbers. Right, let's now move on and look at some examples. I've got two examples. The first example is that relationship between two variables is in the form of y equals kx to the power of n. And so k is a constant, n is a constant, and x is a variable. And then in my data I've got x and y, and they're both recorded. And I want to verify kx to the power n is appropriate. That's the first thing. And then find approximate value to k and n. Right, the first thing we could do is let's take y equals kx to the power n, and let's take the logs of both sides. And then we can separate them out using the multiplication law. And then use a power law, we bring the n down. And now let's write this in terms of the variable y and the variable x, because those are the variables that are given to us. So I've got y equals n log x, so I brought this part down over here, plus log k. Log k, so this essentially is in the form of y equals mx plus c. So this part is your y, n is your m, your gradient, and x is like your log x, and c is the y-intercept. So what this means is, if we were to if log y is plotted against log x, then this is equation of a straight line, and the gradient is n and the y-intercept is log k. So let's look at what that looks like. And what we have here is, if you look at the table, we take x, here's the x values, we find the log of x, and we're given y, we find the log of y. We plot the log of y over here on the y-axis. So this is like a new y, and you plot log x, and this is on the x-axis. We then use the graph and take some readings. We take 0.3 as the y-intercept, and we just take some two general points, and we see that the change in y and the change in x is 0.18, 0.36 respectively. So since firstly, if you go back to the question previously, we wanted to find out if y equals kx to the power n is an appropriate model. And so since we have a straight line, it is an appropriate model. Had it not been a straight line, it would not be an appropriate model. Now the gradient is just changing y over change in x, and we can see that it's a negative gradient, so that gives us minus 0.5. and then the y-intercept is given by 0.3, so the log of k equals 0.3, and since the log of k equals 0.3, we can now rearrange this. This is base 10, and so we can write this as 10 to the power of 0.3 equals k, and 10 to the power of 0.3 roughly equals to 2. So therefore we know what n is, and we know what k is. So this y equals kx to the power of n can now be written as y equals 2x to the power of minus 0.5. This minus can now be written as 1 over, and x is 0.5 is x to the power of half, which means it's a square root. So you've got 2 divided by square root of x. Let's move on to the second example, and this time we've got a relationship where you've got q equals ab to the power of p. Now p and q are my variables, and just notice the difference. In example 1 you had y equals kx to the power n, where x and y were your variables, but now the variable is actually p, so the variable is a power, and the other variable is just your q. So it's a slightly different setup. So again, we're going to find out if it's appropriate. So we'll do the same thing. If it's a straight line, it's going to be appropriate, and then we'll have to use a graph to find values for a and b. So let's start by taking the logs of this equation, y equals q ab to the power of p, and putting it in the form of y equals mx plus c. So we take the logs of both sides. We can then separate this out using the multiplication law, and then we can bring the p down using the power law. That's gone a bit too fast. Let me just rewind right over here. Now at this point I know p and q are my variables, so I need to write this in terms of p and q. So I'm going to have the log of q equals log b, so I've log bp, so I've brought this part down over here, okay, and p is my variable, plus log a, so that part's come over here. I'll put it in this form so it resembles the y equals mx plus c skeleton. So you got y, that's a variable, m is a constant, x is that variable there, and then log a is just a constant, and this is obviously the m is a gradient and the y-intercept is given by log A, and log B is the gradient. So what this means is if log Q is plotted against P, then this is the equation for straight line with gradient log B and intercept log A. Now this is what it looks like, and since the graph is approximately a straight line, Q equals AB to the power P is an approximate model. And notice we, from our equation that we had, if I just go back, where we have Q, log B, P plus log A, we only needed to find out log Q. So we got P and Q were given to us, and we just found out log Q. And we can therefore see that the gradient, which is log B, equals 1.25 divided by 3.2, so it's change in y over change in x. And then therefore I can write this out as 10 to the power 1.25 divided by 3.2. That approximately equals 2.5, so B equals B roughly equals 2.5, and then the y-intercept is 0.5, and the y-intercept is log A. Therefore, and this is base 10, so I can therefore write A equals 10 to the power 0.5. A equals 10 to the power 0.5, which approximately equals 3.2. So the relationship Q equals AB to the power P can therefore be written as 3.2 times 2.5 to the power of P.